Donc, bonjour à tous. Bonjour, Shadi.
Bonjour.
Donc, nous allons écouter votre présentation de thèse pendant 45 minutes sur la modélisation et la mise à jour d'ontologie interactive, application à la formation par la simulation des gestes médicaux.
Oui.
Et vous présentez en anglais.
Oui.
Ça, et ensuite, on passera aux questions.
D'accord, merci.
Après 45 minutes.
Bien sûr. Donc, je vais commencer. Okay. Good morning, everyone. Good morning, everyone. Today, I'm going to present the work performed during my PhD thesis entitled Interactive Ontology Modeling and Updating Application to Simulation-Based Training in Medicine. The thesis is supervised by Rousset and Fabrice Jouanot from University of Grenoble, Alpes, and Loic Druette from University of Lyon. In this thesis, we focus on ontologies because they are omnipresent in different domains with various applications. Ontologies formalize the knowledge of a domain in a conceptual model, which is then shareable by domain experts and at the same time processable by machines. Example of mainstream ontologies in the industry are Yago, Google Knowledge Graph, which is about everything searchable in Google, and also in medical domain, there are examples such as gene ontology, which is a unified representation of biological systems. Ontologies need to be constructed, and this construction has been addressed traditionally by varied techniques and methodologies whose main approach is to combine text mining and knowledge elicitation from experts. The majority of these methods solely focus on well-defined and well-documented domains, such as genomics or encyclopedic knowledge, like the things in DBpedia. However, this approach are not well adapted for ill-defined domains where formal models do not exist, and also a little standard documentation is available. Also, constructing ontologies whose knowledge evolves over time is a challenge for state-of-the-art methods. By focusing on these challenges, the goal of this thesis is to develop methodology and tools to support the construction and updating of ontologies for ill-defined and evolving domains. As a case study, we dissect in the domain of simulation-based medical training. In general, medical simulation is a technique to amplify or replace a real patient experiences with supervised and guided experiences, and has a motto that says never the first time on a patient. As an example, we observe in this figure that which is a simulation learning unit, that a tutor learn to students how to interact and how to do a medical process with a mannequin. This case study is a part of a collaborative research project between a governmental project called SAMSE, the Dune CIDES 3.0 project, which is a e-learning platform, and the Grenoble Informatics Laboratory. Following our goal, we contribute the following interactive and incremental ontology modeling approach. Our approach comprises of 5 consecutive steps. Ontology bootstrapping is the first step with the goal of initializing the core structure of the ontology by employing a few available documents provided by a limited number of available experts. Given the core ontology, the second step is to design and disseminate an online questionnaire to collect more information from the experts. This leads to the third step, whose aim is to enhance the core ontology using the results of the online questionnaire. This enhanced ontology is the input to the next step, which is the automatic generation of a GUI for ontology update. This GUI enables the expert to enrich and populate ontology by interacting with the interface. In other words, we start from very scarce documentation, which is the characteristic of ill-defined domains, and end up with an enriched and populated ontology, which means for the experts to interact with. Our approach consists of our two contributions. Our first contribution for incremental ontology engineering is knowledge elicitation and formalization of ill-defined domains. The outcome of this step is an ontology called OntoSamSay for the domain of simulation-based training in medicine, whose methodology is published in KEO 2019 and VETAI's 2021 conferences. The second contribution for interactive ontology update is the automatic construction of pre-filled graphical user interface, or GUI, guided by an ontology. The outcome of this step results in a generic and interactive GUI for ontology updates called EOP. The work is published in WISE Semantics and VEDA 2021, the year 2021. In the rest of this presentation, we delve into our approach and present the details of the 5 steps that we just mentioned. First, we start introducing ontological languages that we considered in this thesis, then the first contribution, then second contribution, and after that, we present the evaluation for the contributions that we had. And last, we conclude and provide future directions. Let's start with the ontological languages that we considered in this thesis. An ontology is a set of ontological constraints on a domain vocabulary. There exists ontology language standard recommended by W3C, both for defining domain vocabulary and ontological constraints. RDF standard is a graph data model for representing and structuring data and metadata, and is used for defining domain vocabulary. RDF schema also describes hierarchies for properties and classes of RDF resources, and all is a standard language to publish and share ontologies. Both RDF schema and all language are defining ontological constraints. These are the ontological constraints we considered in this thesis. RDF ontological constraints such as class specialization, property specialization, domain and range restrictions, and all ontological constraints such as value restriction, one-off restrictions, and coordinate restrictions. Here is a shortened syntax for them and the semantics. Instead of explaining in details what is the semantics and the syntax, I illustrate it by example. Here I illustrate an example of RDF's ontological constraints in the context of COVID-19 domain, either in a set of shortened syntax or by a constraint graph representation of them. There is a property called has symptom that has a subproperty that is a subproperty of has medical issue. This property has the class disease as its domain and class symptom as its range. And class symptom also has a subclass of named chronic symptom. We provide 2 examples from all ontological constraints in this slide and the next one. The constraint graph and also its represented shortened syntax express a has value constraints to produce the restriction class coronavirus disease, for which the property transmitted by must have at least one value semantically equal to respiratory droplets. And respiratory droplets is the instance of aerosol transmission class. The second example is a minimum cardinality restriction, which indicates that coronavirus disease must be diagnosed with at least one viral test. As we observe on both representation, coronavirus disease has at least one value equal to viral test for the property diagnosed with. We now present the first contribution, which is ontology engineering for simulation-based training in medicine. Here, our objective is the construction of a specialized ontology that captured the skills of few experienced experts in a particular domain for sharing them with a larger community of trainees and to train the less experienced experts in the domain. We discussed this objective in the context of the nascent domain of simulation-based training in medicine. The main issue in capturing the skills in this domain is that the expertise is in the hands of a small number of pioneering teachers who have experienced the setting up of very specialized simulation learning units, such as Sutur. Hence, our main challenge is to formalize simulation learning units. The related work covers a plethora of ontology learning techniques and information extraction tools for ontology engineering. However, most of these approaches do not fully adapt to ill-defined domains. One reason is that these methods require ample documentation, which is not the case in ill-defined domains. Also, it is very difficult to obtain examples as training data in these domains. Hence, the important characteristics of ontology engineering for ill-defined domains is the fact that the expertise is not publicly available and is hard to obtain. Among the related work, collaborative ontology engineering methodologies are the greatest fit for ill-defined domains because they involve different actors to compromise the scarcity of resources. In our approach, we are inspired by these methodologies, especially from diligent and open light methodologies. We adapted these methodologies to build OntoSAMSE ontology based on the participation of several geographically dispersed experts with different and complementary skills in all steps of the ontology engineering. In the following, we describe each step of the OntoSAMSE process. In the first step of our approach, we build a core ontology from limited available reported expertise of few experts. Those domain experts have documented just 6 types of simulation learning units. The outcome of this step is the core structure of OntoSAMSE and formalization of those 6 types of simulation learning units, such as suture, blood transfusion, portacat placement, and different type of hygiene. We ratify the most important elements to formalize. For example, targeted audience, learning objectives, necessary prerequisites, required resources, such as human resources, materials, consumables, and simulators, risks incurring during the simulation sessions, and in real situation, and evaluation of the prerequisites and objectives. The obtained general structure of OntoSAMSE reached to 111 classes, 34 properties, and 121 instances. The figure on the left illustrates the part of hierarchy of classes and properties for the core OntoSAMSE. Several properties assign SAMSE simulation learning units as an domain. The property SAMSE resource defines the required resources of the simulation learning unit. Also, the property objectives defines the objective which should be achieved during the simulation learning unit. The objective could be a medical procedure or a gesture, or a medical gesture. Our second step is a knowledge acquisition. Recall that our focus is on the ontology development for ill-defined domains. Hence, our objective in this step is to consolidate the existing ontologies and existing description for the ontology and extend the other simulation learning units. To do this, we teamed up with a pedagogical engineer to design an online questionnaire and disseminate it among health educators in the domain of simulation learning. We have designed the online questionnaire based on the generic properties declared for the 6 simulation learning units described in the first step, that means the bootstrapping steps, with as many sections in the questionnaire as properties to be filled for a learning unit. The figure on the right shows the one example of the questionnaire for the steps that defines the required resources for developing the simulation learning sessions. For the campaign of the questionnaire dissemination, we created a directory listing 1,223 health professionals and provided face-to-face or remote support to help them in answering the questionnaire. In the course of 7 months, we received 304 responses, representing 25% return rate nationwide. To provide ample expressivity for the experts, we let most answers in the subjective parts of the questionnaire, here, to be of type free text. The advantage of this design choice is that experts do not go through the burden of selecting options among the list of choices, and they can and hence they can just express their knowledge whatever they can. To alleviate the irregularity in the experts' responses, we employ some techniques from the domain of natural language understanding, or NLU, namely non-phrase extraction and part of speech tagging or pose tagging, to find commonalities between their answers. By employing the aforementioned NLU techniques, we grouped the answers actually per each simulation unit to identify 77 different simulation learning units, within which 24 were described frequently by the different professionals. Our third step is ontology enhancement. We improved and refined the core OntoSensei ontology by modeling commonalities between the simulation unit described by different professionals in different parts of the questionnaire. The resulting ontology is a hierarchy of classes and of properties enriched by ontological constraints on the properties and on the classes that convey the constraints that will have to be fulfilled by their future subclasses, subproperties, or instances. The enhanced structure of OntoSensei, using the result of the online questionnaire, reached 470 classes, 49 properties, 550 instances, and 700 constraints. We made the final version of OntoSensei publicly available in this link via the website data board, which is the repository, dataset repository. In the next slide, we show several extraction of different parts of the resulting ontology. OntoSensei is modeled by using an online editor and visual modeling environment called Top-Rate Composer. Here we illustrate a part of the specialization hierarchies of properties and classes resulting from the RDFS ontological constraint declared in OntoSensei. We highlight additional classes and properties compared to the hierarchy of classes and properties from the core ontology, from the first step, actually. The hierarchy of, we observe here there exists 24 added classes to the simulation learning units. Moreover, the enhancement process has resulted on creation of new classes, such as Samsei knowledge, which is describing the knowledge bearing the specialities of the learning unit, and Samsei content that describes docimological and pedagogical content, such as the different type of evaluations, the courses, and medias. We also note that there exist properties which specialize several other properties, such as Samsei resource, which is specialized in equipment supplies, human resources, and simulator resources. The center part of the figure demonstrates a part of the all ontological constraints we considered for the class port ACAT placement. This simulation learning unit, port ACAT placement, is a simulation learning unit which educates students for placing a port or a catheter, like in the picture. The demonstration is in the syntax proposed by top-rate composer. The all ontological constraints declared for this class is all minimum cardinality and has value. Among the list of all ontological constraints declared for class port ACAT placement, we now provide two examples. The figure visualizes the RDF constraint graph corresponding to the RDF shortened syntax shown below. The Samsei strill compress, which is the instance of the class bandage material, is declared in the ontology as a mandatory value of the property equipment supplies for the class port ACAT placement. Note that the illustrated graph is enriched by some RDFS ontological constraints such as subproperty of, subclass of, and also the RDFS label and RDF type. The second example is on the minimum cardinality constraints declared for the property equipment supplies and the class port ACAT placement, which express that at least one value, one equipment of type protective supplies is needed for the simulation learning unit port ACAT placement. This wraps up our first contribution, and now we move to our work to interactive ontology updates. Our main focus here is on the fact that ontologies evolve both in their structure and in their content. Hence, it is crucial to keep them updated via an ontology update process. Ontology updates encompass both ontology enrichment and ontology population. Ontology enrichment means to extend an existing ontology with additional concepts and semantic relations. On the other hand, ontology population is the process of adding new instances of concepts to the existing ontology. In the literature, ontology updates in domains with non-documented knowledge are often performed in an exploratory and manual fashion. This is particularly the case where domain experts with limited knowledge of ontology language aim to update their ontology. This manual process is, of course, cause errors in their updating procedure. To tackle manual updates, we face two major challenges. First, it is often troublesome to represent the graph-based nature of ontologies to domain experts in an intuitive and comprehensible way. Beyond the representation, the second challenge is to enable the update process for these actors without the knowledge of ontology languages. Our solution to tackle the aforementioned challenges is to contribute an interactive ontology update ecosystem via the automatic construction of a graphical user interface, which we called EOP. We leverage web page as a natural interaction means to tackle the challenge of counterintuitive ontology representation. EOP generates and pre-fills the web page from ontological constraints, which supports the controlled update process of a given ontology. Our interactive ontology update approach, EOP, consists of two consecutive phases: ontology-based GUI construction and transformation of the GUI interactions. In the first phase, the RDF data and the ontological constraints of a domain ontology are automatically transposed into a GUI using a set of mapping rules that I will explain in the future slides. The expert explores the automatically pre-filled web forms and provides additional data in case she needs it, she finds it necessary. In the second phase, the input entered by the user in the GUI is transformed into RDF graphs using a set of binding rules, which I will explain also in the future slides. The generated RDF graphs will be validated by an ontology experts before being permanently added to the ontology. We now focus on the first phase of our interactive ontology update approach. We developed 16 mapping rules in declarative approach to construct a GUI guided by ontological constraints. Each mapping rules maps RDF constraint graph from the domain ontology to the web form layout, which is described by an ontology that we created and called EOP web. The result of mapping rule in the form of an EOP web graph provides the full RDF specification of pre-filled web pages. The EOP web ontology is organized around 4 main classes: EOP page layout, EOP page, EOP container, and EOP widget. The widgets are the direct point of user interactions associated to the RDF graph for the input ontology. The figure on the right shows the web page layout template filled as a function of the EOP web ontology and the ontological constraints. To better understand the mapping rules, let's focus on an example. Here is the general model for one of the 16 mapping rules that we proposed for a chosen focus class F on the property P and on class C, and this is a minimum cardinality constraints. The mapping rules will be instantiated for each constraint as shown here for this mapping rule. Here is the RDF constraint graph for the class portacat placement, which conveys that at least one equipment of type protective supplies is mandatory for simulating a placement of a port or a catheter. This constraint graph is mapped to the following instantiated graph of the EOP web ontology. The implementation of this graph as an automatically pre-filled web pages is shown here. The web page is dedicated to the property resource for the simulation learning session of portacat placement. The resource protective supplies has several subclasses, which are represented in the form using the widget tree view. By clicking on each subclass, the property EOP hidden becomes false, and consequently, the widget EOP list box shows the instances of the selected subclass. The experts can interact with the GUI by either selecting one or many of these instances or entering new ones if it's needed to populate the ontology. Now we focus on the second phase of EOP, which is the transformation of interactions. In order to update the ontology with interactions made by the experts in the GUI, we developed 9 different binding rules, which transform those interactions into RDF graphs. Each binding rule binds user interactions in the form of EOP web graph pattern to the RDF graphs to be added in the RDF graph of domain ontology. We'll show an example in the next slide. The triggering of a binding rule happens when an input is entered by a user in the GUI. Here's an example of several binding rules. For clarity purpose, we replace the EOP web graph pattern on the left side of the binding rules with its corresponding web form representation. We follow our example from the mapping rules and show the interactions that the user, that experts did on the page for the property resources of the session PortaCat placement. The very first interaction of the expert is when she chooses a simulation learning unit to observe and to explore. This interaction is bound to the following RDF triple to be added in the RDF graph. The triple describes the creation of an instance of type class PortaCat placement, and the name of this instance is PortaCat placement number 3. We move to the next interaction where the expert provides when the expert provides a subclass from the protective supplies classes and check the disposable drape from the hierarchy of protective supplies and select an instance of this disposable drape, which is simple disposal drape. And these interactions are bound to the following RDF graphs, which adds the instance of this instance of simple disposal drape to the simulation learning unit of PortaCat placement number 3. Then the next interaction is where the expert provides additional supply called antibiotics. To enrich the learning unit PortaCat placement, he can enter new data like antibiotics. This interaction is bound to a new constraint, which indicates that there is a need to have at least one equipment supplies equal to antibiotic for this learning unit. Last but not the least, we show another binding rule which enriched the domain ontology. The expert provides the number of required resources for the simulation, for the simulators such as Venus Access Chest Simulator Minocan. For example, he can enter number 2, which is then bound to a minimum cardinality constraint for the property simulator resource, describing that there must be at least 2 Venus Chest Simulator Minocan for this simulation learning unit. This wraps up the contributions, and now we move for the evaluation of our approach. For the evaluation, we considered 3 different objectives which encompass different aspects of our contribution. First, we measure the usefulness of EOP interface in enabling experts to populate and enrich the ontology we developed for simulation-based training called OntoSamSay. Second, we focus on OntoSamSay and evaluate its quality through its presentation by the GUI. We also evaluate the generality of EOP to domains other than simulation-based training to see how it can be adapted to other ontologies. We first discussed the setting employed in our experiment. Given the interactive nature of our approach, we employed user studies to observe how experts use EOP. We employed a group of 22 medical experts in our study. This group is a subset of group that we solicited 1 year prior to the user study to perform the enhancement step for OntoSamSay. The protocol of our user study consists of 2 consecutive steps, interaction steps and evaluation steps. In the interaction steps, experts logged into the GUI with the with a credential, select a simulation learning unit, and begins to observe and update the desired simulation learning unit. In this step, not only we record the interaction, we also keep track of more data and metadata, such as the total time spent on updating a training session and the total number of interactions. Once the expert is done with updating the web pages of one training session, she moves to the next step, which is the interaction step. In this step, the expert responds to a survey which evaluates some qualitative aspects of EOP and ontology onto SAMSE. For a more granular analysis of the experts, we group them based on first, the number of interactions they did with the EOP, and second, the duration of their interactions. This table shows the distribution of the experts in these groups. Based on the number of interactions, we grouped experts on prolific experts with the interactions, with the average interactions of the above 6 interactions, the active experts, which is the between 3 and 6 interactions, and moderate experts, which is less than 3 interactions. Also about the duration of interactions, we defined a group of short-time experts whose average interaction duration is less than 2 minutes, the group of medium-time experts that is between 2 and 4 minutes, and the group of long-time experts which more than 4 minutes of interactions. That being said, we start our result. In the first objective, our main is to evaluate different aspects of EOP. In the interest of time, we only present the results for the aspect of added value, which is the subject of this slide, and expert satisfaction, which will be discussed in the next slide. For our experiment on added value, we pick top rate for the comparison. We employ 3 different ontology editing tasks and measures the number of interactions required to fulfill these tasks. The tasks are categorized on 3 different levels based on the cognitive effort required by the experts to fulfill these tasks. The results shows that the number of interaction steps increase with the difficulty of tasks for both tools. However, the trend for EOP grows from 3 to 5, and also the trend for the top rate goes from 5 from easy task to difficult task, that is 21. Our conclusion is that that EOP enables experts to fulfill their task more rapidly by weaving relevant informations together using ontological constraints. Now we deal with the satisfaction of experts when using the EOP interface for observing and updating their specialized ontology. We define the notion of expert satisfaction as a combination of utility, usability, and adoption. Utility is the usefulness of the method to fulfill a given task, and usability is the easiness of interactions with the methods. Adoption also is the usefulness of the method for future similar tasks. We measure these aspects on a Likert scale from 1 to 5, where 1 means very dissatisfied and 5 means very satisfied. While the experiment is performed for all the groups of experts, we here just show a sample of them. We observe that around 82% of the participants have a positive view on the utility of EOP. This appreciation is even more exaggerated for the prolific group, which shows that more interactions smooth the learning curve and increase the perception of utility. Also, the experts perceive usability positively. However, there is a vivid contrast with the general trend for the group of long-time experts, which is probably because they spent too much time to fulfill their tasks and eventually got lost in the process. Last, most experts voted to adopt EOP in the future, with more than 70% on the positive side. In the second part of our experiment, we focus on evaluating the Onto-Samsei ontology. We measured the expert assessments of accuracy and completeness of the ontology through its presentation by the GUI. Accuracy is the precision of information based on experts' prior knowledge, and completeness is the retrieval exhaustiveness of the necessary and required information. Dashboard in all the charts shows the average scores for all the experts. We observed that the majority of the experts are positive on accuracy. However, short time and moderate experts express more negative votes than a long time and prolific experts, respectively, potentially because less investigation in the former groups did not enable them a precise view of the ontology. We also observed that around 76% of the experts find Onto-Samsei adequately complete. Now we shed light on the generality aspects of EOP by showing its applicability on another domain. Given an ontology from another domain, we verify whether EOP is enabled to produce the pre-filled web forms which are meaningful and useful in that domain. For this aim, we employ an ontology called Persido, which contains the structure and information of a dataset publishing and sharing web portal. Here we observed pre-filled web form generated by EOP vis-a-vis of the Persido portal screenshots of the same page. We observed that all the elements in the manual form are well presented in the EOP's output. Moreover, the dynamic structure of the auto-generated forms facilitate change in the future, while the manual form is fixed and needs to be re-engineered. That being said, we move to the conclusion and perspectives. So in conclusion, in this thesis, we proposed a methodology for constructing specialized ontology adapted to ill-defined domains. And we developed a novel and interactive ontology update approach via a graphical user interface. We evaluated our contribution with an extensive user study with the domain experts, where we concluded that Onto-Samsei is perceived accurate and complete by the experts. We also observed that EOP enables the experts to fulfill their task more rapidly by weaving relevant information together using ontological constraints. We also observed that experts have a positive view on utility, usability, and adoption of EOP. Last, we evaluate the generality aspects of EOP and found that the approach can be easily adapted to other domains to capture the semantics relations and handle the evolutions of the domain. Among several futures for this future directions for this thesis, we briefly introduced two. The first future work is about learning mapping rules. We plan to come up with an automatic way to extend the list of mapping rules using the existing web pages or domain-specific intelligent tutoring systems, which are already available for the domain in the form of a supervised learning problem. The second direction is on the automatic validation of ontology updates. In our setting, each ontology update should be first validated by an ontology engineer before being permanently added to the ontology. While this is a necessary step in the constructing of ontologies for specialized ontologies, in more general ontologies, that process can be more robust. Our future direction is to automate the validation process for general ontologies while leveraging the wisdom of the crowd, which means that the experts vote on the updates that another experts already performed. And then if the consensus on an update reached some certain level, it can be automatically added to the ontology without the need of an approval from an ontology engineer. And here is the list of publications reporting the contribution of this thesis. And with that, I'd happy to receive your questions. Thank you.